Okay, let's start. So I want to start with an announcement. We posted this on Ed, but I want to make sure everyone hears it. Because of the class size shift, the campus rooms we got for the midterm are on Tuesday, March 21st from 7 to 9 p.m. Initially, we thought we were going to get Wednesday, March 22nd, 8 to 10, but this is the time we actually have. So this is the time we're going to have the midterm exam. So sorry about the slight change there. The other announcement is you've gone through homework 0, and you're probably working hard on homework 1. So we noticed that the attendance at the homework party was not as high as we expected. So either people are finding it perfectly plausible and easy to do in groups that you already have, which is great, or there might be some issue with the timings of the homework parties or something. So what we're going to try to do is we'll announce it, but we're adding might shift, add/change a homework party to not be in the evening. So we'll have one that the time we could get, it's probably like 9 to 11 a.m. on Thursdays. So an announcement will come out for this to hopefully give people, if they can't make the 7 to 9 p.m. slot that we were able to get earlier, this is more of a daytime slot, so we'll try to have another one for you guys. We might remove one of the others to keep things efficient. So that's one thing we noticed. The other thing we noticed is that the activity that we're seeing on Ed, on some of the questions is, it's all good, but it's a little lower than we had expected for some of them in terms of the kinds of questions that people were asking. So we want to make sure that, if you read a question and you try with your friends, your study group to work on it, to do it, and you find yourself, stuck on something or you don't understand something, it is okay to ask. We don't want people to do I glance at the question, I don't understand something, then I ask, and then 5 minutes later I say, oh, I already got it. Like, that's kind of annoying for everyone else, but like just, if you really have a question and you want to ask something, please do ask. We can support questions that we get. Final kind of announcement is, I mentioned this last time, I'll say it again in case some people missed last lecture. The discussions are meant to be quite useful to you in terms of understanding what's going on. So if you haven't gone to a discussion, please do. It's important for understanding. We have staff there to support you and your understanding of the material. So do take advantage of those. Okay. So that's the kind of logistics type announcements that I wanted to make. I did get some questions and feedback from people that and I felt the last lecture I kind of went really fast at the end on things. So I'm going to slow down and kind of cover it. So as a result, I'm going to change what I'm going to do today a little bit. Instead of kind of what I initially announced that we would launch into kind of a broader survey of architectures and things, we will push that to Monday. And today we're going to kind of keep going kind of at the level of preliminaries to make sure you understand those. In doing this, I'm counting on the idea that most of you, the idea that neural nets are useful and can be used for lots of different problems is not something I need to tell you. If, however, you're one of the people who really hasn't looked at this at all and doesn't know, and you're really, really curious, you do come to office hours and I can say something about it. But otherwise, we're going to kind of talk about the survey of architectures and things like that on Monday instead of today. Today, my goal is to recap the story and also introduce some language I realized I didn't say in lecture on inductive bias. I want to then talk about the thing I mentioned. I posted something on the Ed for the lecture, kind of talk about this 2 views of learned features. It'll engage with what you're doing in the homework. One of the views will engage with doing the homework, but the other one will engage with something that you've seen in discussion. And then I want to go in to talk about initializations a little bit and talk about optimizers beyond stochastic gradient descent, which is the one that we've talked about so far. Just because I think these are like preliminaries that are good for you to know when engaging with the rest of the class. Okay, good. And so at the beginning here, definitely I want to make sure everyone understands everything. So throughout, I want everyone to understand everything, but at the beginning, I want to make sure that these things are familiar to people. Oh, I shouldn't have done that. Okay. Nice. So what's our big picture strategy to understand neural nets, right? The one that we're going to follow and people generally follow is, as I mentioned before, we look where the light is. So we understand something, and then we try to leverage that to understand something we don't understand. So we want to understand simple linear models. And then you want to use that to think about nonlinear models. And the tool that I mentioned last time to do that at the end was how? We try to think about local linearization. It's how you bridge between linear and nonlinear things. Why do we do this? Do we believe this will explain everything? The answer is no. We have evidence to say that there are things that are missing in a picture of what happens in nonlinear models by only looking at local linear models. This much has been established. There are phenomena we cannot explain this way, but we know how to do this, and we don't know how to understand some of those things except empirically. So you should know how we can leverage the intuitions that we can back up, and then as we go, we'll introduce others. Okay, so when I say simple linear models, in the context of machine learning, the simplest one that anchors most of our understanding is just least squares. So I mentioned this before, just talk about it again. I'll use notation that looks like this. There's some weights you want to learn. There's some data points, and you want to match something. So again, let's just mark the types of everything. This is all hopefully review. There's D features. There's D weights we need to learn. We have N data points. I arrange them in rows for the covariates. And this is N long. And so we mentioned last time that we have, for ordinary least squares, we try to learn these weights by computing the argmin. Of y minus xw squared. And for ridge, we add a regularizing term. So we have the original loss term, and we add a regularizing term. So in discussion, you saw, so in homework, you were asked to kind of grind through and think about lots of different perspectives on this. But in discussion, you saw also that this perspective versus this perspective can be understood as, from a probabilistic backstory, as this is a maximum likelihood estimator, and this is a map estimator. Right? Where the difference between the two is that in the maximum likelihood estimator, you have no prior on the weights W, and here you put a Gaussian prior on the weights W. right? That you saw in discussion. And so you remember how that works is you look at, when I say in the probabilistic backstory, you say the reason these two aren't exactly the same is that there's some noise in my observations. That noise is distributed IID Gaussian and then when I say a maximum likely estimator, I said I want to pick the estimate for W, which corresponds to the most likely noise estimate that would have given rise to my observations, right? And then because the Gaussian has these densities that are, spherically symmetric, you get this, because Y minus XW is the hypothesized noise, right? So just again to connect a discussion a little bit between what we said in lecture. And the reason you get this additional term when you have map is that if you look at Bayes' rule, you have to multiply the conditional by the prior, right, in the numerator, and then you get a denominator term which doesn't matter for the argmax, and this is coming from the prior, right? How likely is the W? What's the probability of the W? Okay, so this is hopefully, both review, connecting to discussion. You should understand it. The probabilistic interpretations of machine learning, I believe, are standard in most machine learning courses, so this should be review. Now, last time, and this is where I'm going to slow down because I think some people didn't understand what I was doing. You have formulas to solve these. So for this, right, you have the OLS formula, which is so you can have W hat. I'll mark it OLS to tell you ordinary least squares. It can just be computed explicitly as X transpose X inverse X transpose Y. Now, for Ridge, and the homework has you also engaging with this, so it's fine. I'll take a different tack to hopefully exercise some other skills for you. For Ridge, the formula that we talked about was X transpose X plus lambda I inverse X transpose Y. But you saw in, I think this wasn't in discussion, but it's on the homework, there's a second formula. Which goes like this. So you have two different formulas for the solution to Ridge. Okay, so equivalently, these two are equivalent formulas. So now I'm going to ask people this question. So this shows up on the homework, right? How many people, I'm going to restrict attention to people who took 189 at Berkeley. How many people who took 189 at Berkeley saw both formulas? Okay. How many people who took 189 at Berkeley did not see both formulas? Okay, so probably if you didn't see both formulas in 189 at Berkeley, it was like you saw this one and you didn't see this one. Okay, so how many people, now I'm going to restrict attention to people who had a machine learning course elsewhere. Had a machine learning course elsewhere. How many of you have seen both formulas? A couple of you. And how many of you who took a machine learning course elsewhere only saw this one? Okay, so it's a sizable fraction of people who haven't seen this formula. So it's probably worth thinking about it a little bit. So first, let's just get the types of everything. We talked about it last time, but I'm going to do it for both cases again. This matrix here, what's its size? How big is it? Someone just call it out. This is n by n? D by d, right? It has to be because this is d dimensional, right? So it better have d different rows. And so because it has an inverse, it better have d columns. Okay? Y is n-dimensional, and so X transpose bridges between those two dimensions here. Okay, here, what's the size of X transpose plus lambda I? N by n. Okay, so this is sometimes you call the normal form, the standard normal formula for ridge. Normal also because these are called sometimes the solutions of normal equations, right? And this is like in that same style. This is alternatively, this has a few different names in terms of how it's called. One is called the dual perspective on the solution to ridge. The other perspective on this is called kernel ridge regression. Okay, so this is also called kernel ridge. Okay, so at this point, I want to do, so yeah.
So this is the solution to the dual problem or the minimization problem?
It can be thought of as coming from that perspective. I mean, it's a solution to, it's still giving you a solution to this, right? But this can be viewed as what solution you'd get if you took a dual point of view to solving it. Yeah. So if you look at, but let's just, I want to make sure that, again, just because it's good to review some things. So again, I'll ask again for a survey, how many people have seen this thing called kernel ridge regression? Raise your hand. Okay. So maybe I'll step back and ask a question. I believe that kernel approaches to doing machine learning are standard in all basic ML courses. So for those of you who haven't seen this, can you raise your hand and tell me how you saw kernel approaches introduced to you? Or, yeah. Go ahead.
Yeah, I did SVM's kernel approach.
Okay, so you saw it via the kernel approach to the SVM.
Yeah, but not here.
Not here, yeah, elsewhere. Yeah, it's totally fine. I mean, that's often, it was the kernel approaches to the SVM that really transformed the field in terms of people's use of kernel approaches in practice. And so it's, from a practical perspective, it's very natural to think of to teach kernel SVM. Kernel SVM is a lot more complicated than this in terms of the derivations. But it's harder to teach that. But practically speaking, it's more useful. Anyone else? Did everyone else who saw kernel methods without seeing this, see kernel methods introduced directly in the context of the SVM? Yeah? Okay. In my experience, people who've gone through that treatment often, I'd say with 50% probability or higher, get lost in the weeds of what's going on, and sometimes the big picture gets a little bit lost. So I think it is worth kind of, for your general knowledge, to talk a little bit about this to make sure that everyone's on the same page. Okay, so why is this called the kernel ridge formula? Why does it have this? Like, why is this? What's the connection? So for this, I want to first make sure that you can see how these formulas reveal something different about what's going on. So they're equivalent. In this formula, you see that, look, what I see here is a modification of OLS. The connection to OLS is very tight here. Right? You can see it's basically OLS, except you have this lambda I, which is like changing how you weight different things, right? So what does this formula reveal about the nature of the ridge solution that is not visible here? So I want you to observe, I want to ask you a question. When you do this multiplication, what is the type of the object that you get back? A vector, right? It's a column vector with, how big is it? It's n, right? It's an n-dimensional column. Okay. Matrix vector multiplication gives a linear combination of the columns of this object, right? That's what matrix vector multiplication means. So, what are the columns of X transpose? The data points. Okay? So, this tells you something, reveals something that isn't obvious when you look at this, which is that the final weight that you learn is a linear combination of the data points. Right? Do you see that? Okay? So that's interesting. And something which should not be surprising to you, and we'll talk in a moment about thinking about how gradient descent works and how stochastic gradient descent works. Okay? But it's useful to you to have the ability to understand what's going on from different perspectives. Okay? It's very important to understand things from different perspectives. So, okay, it's clear. This now reveals to you that the ridge weight you learn is a linear combination of data points. Okay? Good. So why is it called kernel ridge? So to understand why it's called kernel ridge, we can interpret different objects. So first, so we know the interesting thing about this. Okay, good. This guy, XX transpose. Let's just start going over here. What is XX transpose? What's its size? N by N. Yeah, good. It's a matrix. What does it have in the ijth position? What's inside this thing? Yeah, it has inner products between inputs. Right? It's the matrix of inner products. So it's this aspect of it, which is why it's called kernel ridge, from the perspective of practical use, right? Because when you learned about kernel approaches to machine learning, the general philosophy you learned is anywhere you have a matrix of inner products measuring, you think of that as a similarity measure between inputs, and you say instead of dropping in a matrix of inner products, the Euclidean inner products, drop in any other similarity measure that you want that satisfies positive definiteness, whatever, right? And just use that, right? So by having the formula in the form that makes this fact that this inner products are at the heart of what's going on, kind of pulled to the surface, you can see exactly how to do that, right? Here, X transpose X is not a matrix of inner products. So this formula does not show you how this might have anything to do with similarities between points, whereas this one does. Okay, so that's one connection to kernel methods. Is that clear to everybody? Okay, good. Next thing, why is this called called kernel ridge? It's like a 5-minute review. So it's because on test points, the thing you need to compute is, of course, W hat ridge transpose X. Right? This is the thing you have to compute, right? Or, alternatively, this is the same as saying X transpose W hat ridge. Right? Because it doesn't matter the order which I do it. So when you do this on test points and you substitute in the formula, this one, what you see is you get that, right? Just substituting it in. So first, what is this object? What kind of a thing is it? Right? What kind of vector? The row vector. So this is a row vector. What are its entries? What's its first entry? Yeah. So X transpose, remember, consists of all the different data points. So this is the dot product with all the training points. That's another reason it's connected to the idea of kernels, right? How do you use kernel methods? You take a test point, you say, how is this related to all of my training points? How close is it? How similar is it to all of my training points? I will use that to weight something, right? So that's why this is called kernel ridge. Yeah.
You make the same argument with the min-norm solution.
Excellent question, right? The question is, does the same argument go through for the min-norm solution? The answer is yes. That affects, maybe we'll just jump immediately to thinking about that. In a way, this thing's spirit is actually like the min-norm solution. This looks like the Moore-Penrose pseudo-inverse in this shape, right? So everything we're saying is connected. So now in the homework, we ask you to show that this and like implicitly that this and this are the same thing, right? It's one part of the implicitly in the homework. So I'm going to ask you guys to spend a little bit of time on a piece of paper. I would like you to show that these two are the same, except I'm going to tell you a particular tool to do it, right? That's probably not the one that you thought of using on the homework. So I'm going to say exercise, in-class exercise. Use the SVD of X to show that. Okay? Everyone understand the question? This thing and this thing are the same thing. They give the same answer. Use the SVD to see it. Now, why am I telling you to do this? Because actually, when you look at these formulas, you should be troubled or potentially troubled by some things, right? So let me first tell you what you might be troubled by. If these two formulas are equivalent, they behave the same for all lambda, right? Which means they behave the same for lambda going to infinity or 0 also. Does everyone see that? Okay, now, either, in this case, you're thinking of D, because it's a least squares problem, D you're thinking of as being smaller than N, right? So N by N is bigger than D by D. Everyone see that? Okay, so hopefully people are beginning to feel a little knot in your stomach mathematically, okay? So this d by d object is like happy and probably full rank, right? Adding a lambda I makes it more so. All good. This n by n object is probably not full rank, right? Does everyone see that? And so adding a lambda I makes it happily full rank, right? But when lambda goes to 0, this guy is approaching a singular matrix, and you're inverting it. So why is it that this thing blowing up doesn't cause these two to become different? Do you see that? Not numerically, but kind of just even mathematically. Do you see that? Okay, I want to make sure everyone understands. Like, this is like, as you navigate deep learning and machine learning, you're going to need all of your different intuitions kind of to be in play, because you don't understand what's going on. So you need all of your senses to be active. And one of those senses that should be developed is your mathematical sense, right? Your mathematical intuition, or spider sense. Like, I sense danger, right? And then you have to think, is this danger real or not, or something? And that will help you understand what's going on. So in this case, like, if you do it this way, you will not get as lost in a sea of algebra, and you'll understand why this is safe. Okay, so take 3 minutes and try to do it. I'll check in. How are people doing? So raise your hand if you're done. Okay. Raise your hand if you're making progress but not done. Raise your hand if you're stuck. Okay, so I'll give you a couple, one more minute to people. Okay. I'll just bring everyone back together. Okay, so hopefully you've, anyone still working? People are mostly done? Okay, good. What you've seen, right, is that as you kind of just use this fact and use this, what these objects are like, right? So what happens is that when you apply the SVD, you just change the SVD coordinates, so all the coordinate transformations just fly out of the inverses and everything together, and then you get everything, just all the things will cancel out, right? And you get a story that's essentially entirely in terms of sigma. And you look at, inside here you have a sigma transpose sigma, and here you'll have, a sigma transpose. And you look here and you have a sigma sigma transpose, and then you have a sigma transpose over here. But sigma transpose sigma and sigma sigma transpose essentially are just different sized things that look identical inside. You have, whatever the rank of x is, k, you have that many things on the diagonal, and you have zeros everywhere else. And so what ends up happening is that when you add a lambda I to it, you just get a lambda added to all the diagonal. And when you take its inverse, you get identical things for both of them, just different sizes. Right? Then, the key is that the only thing that ever comes out of this, right, is what happens to y hitting those singular directions that are actually represented in x, right? So x, so the singular vectors v are the ones that correspond to non-zero singular values, are the ones that span the column space of x transpose, or the row space of x. And that's where your data points are. And that's the only thing that ever actually moves through this thing. So anything that's happening elsewhere doesn't matter. So even if this thing is hypothetically blowing up as lambda is going to 0, the directions in which it's blowing up never make it through X transpose, which is why that's safe and why this equivalence holds. Okay, so hopefully you got something out of doing this exercise to understand why these are equivalent. Also, this should confirm to you that when in doubt, use the SVD to understand what's going on. This should be a lesson that has been hammered into you from earlier classes, but that's why, because it's what we know. We know how to understand it. It makes things, we can understand what's going on. So it's useful here too. Any questions on this little exercise and why this is equivalent and so on? Okay, so I think in the next homework, we will put something in to further deepen your understanding of this object. So in the Gaussian, I'll just mention it briefly. In the Gaussian setting, if you look at this thing, right, this is like map estimation for things that are Gaussian, with a Gaussian prior on W and Gaussian noise in your observation, and X something, just some data points, wherever they are. It's an interesting fact that for Gaussians, the map estimate is also where the mean is. So you can look at a conditional mean. This is hopefully a fact. So if you look at a conditional Gaussian, a Gaussian is maximized at its mean, right? So Gaussian density is maxed at the mean, which means that map is the same as estimating the mean, which is the same as mean squared error estimation. So it turns out, and you'll be asked to do it on the homework, is you can view this as actually just an MMSE estimate using a standard MMSE estimate formula for Gaussians. Again, different perspectives are good to have to understand what's going on. Okay, so hopefully all this is a little bit clearer to people, understanding ridge, understanding what's going on. So just one comment here is if you do this, you could also view the ridge formula in sort of outer product form. So if you just grind through this calculation, right? I don't know if everyone did this. At ridge. You can write it this way, in outer product form. I don't know, how many people, when you were showing this was equal, went all the way to something like this? For both sides? Yeah, one person. Okay, so a couple of people. Yeah, you can just, this is like another nice way to see what's going on. Shows you why this is a linear combination of the things expressed in the subspace of this, and how the singular values show up in doing this. Okay, good. So now, I want to say a little bit of what I was saying before, except maybe a little slower. So there's a term that we use, which is inductive bias. This is a term from philosophy. And what it means is that we're doing learning, and we want to see what kinds of things will we actually learn. Like, what is our bias? What kind of patterns do we actually learn? And what I told you before is that it's not enough to think about you can learn any pattern. You can express any pattern using your neural net. You want to know what are the actual patterns you'll actually learn from data. So that's where the idea of that's where the term inductive bias comes. So last time we talked about how gradient descent has an inductive bias. Let me just close that off. By itself, gradient descent has an implicit inductive bias. That is not misaligned to ridge. So if you just look at gradient descent for OLS, we did this last time, but I want to make sure I went fast, so I want to make sure that everyone understands it. Let's look at OLS, right? What you have is the update at the next time for your weights that you're learning is the weights you learned last time, plus, I'll just use 2 because I didn't put a half, 2 eta x transpose y minus x wt, the residual. So, remember, we said that one of the nice things about the ridge formula is that it shows you that the learned weight is a linear combination of the inputs. Looky here. The update to the weight is a linear combination of the inputs. So if you start at 0, for example, and always add only linear combinations of your data points, where are you going to be? Some linear combination of your data points, right? So that's nice to observe. I didn't talk about it last time, but you can hopefully see that here. So we said that if you look at this in SVD coordinates, so just, this is gradient descent for OLS. If you do stochastic gradient descent, where you only use a batch, what changes? What changes is this and this, right? Your batch is a smaller, so you look at the residuals only on a smaller set of data points, and you only look at those data points inputs, but otherwise the formula is identical. So useful fact, SGD also only moves in this subspace, not just gradient descent. SGD also only moves in this subspace. Okay, so, but going back to gradient descent, because there we can think about the SVD, right? We said in SVD coordinates, and we said it last time, but I didn't let you guys ask questions about it. So let's look at the ith position in SVD coordinates. This is equal to the scalar. This is a scalar now. I look at the ith coordinate in SVD coordinates. To eta, and now everywhere you have an X transpose, you're going to have a sigma transpose, which is diagonal, which means you can just pull out the relevant sigma. Sigma I, and then the scalar residual in this coordinate. So this will be talked about in the discussion because it's super important. I want to make sure everyone understands it. And you get this kind of thing, which I can also combine these terms. 1 minus 2 eta sigma I squared. Okay, so everyone see what I did? I just wrote that formula down. I wrote it out as a recursion, in a form that made the relevant eigenvalue of the dynamics very clear. Okay, so last time I talked about this, but I want to make sure that everyone understands it, because I think some people didn't get it. In SVD coordinates, you can see that what's happening is every single singular direction is doing its own thing. There's no coupling at all if you're doing full gradient descent. Everything is converging to where it should go, and all of them have their own evolution. Is that clear to everybody, first, of what the implications of this are? We wrote that last time. I want to make sure everyone gets it. Clear? Okay. Now, our learning rate, eta, step size, is some number. So, look at this. Suppose eta is small, some small thing. For what kind of singular value is this quantity close to 1? 1 minus 2 eta times sigma I squared. When is this close to 1? When sigma I squared is close to 0. Is that good? Everyone's good with that? Okay. So what's the other interesting thing this could be like? So this thing has to be stable, so it's somewhere in the unit circle. Everything is real, so you don't have to worry about real numbers. Okay, so there's two interesting places. The boundary, close to 1, that's when sigma I squared is small. What's the other interesting thing this could be like? 0, right? Because 0 is super fast, right? This thing is like something which will decay as you exponentiate it. So it disgoverns the speed of convergence. Clear to everybody? Like, if you look at this, the evolution of this kind of thing, there's some asymptotic value you'll tend to, and then you'll go to it like that, right? And how fast you go, the time constant associated with this is tied to this guy, right? So you go like this, and you'll go faster and faster the closer this thing is to, the whole thing is to 1. What does that mean? It means that large sigma I squareds will converge faster. And so hopefully, you know this other fact, that if you have exponentials, from the perspective of different exponentials, one of them has already completely converged by the time the other is like moving, right? It's asymptotically, right? Exponentials like converge much faster than each other if they're going to converge at different rates. So what this tells you is that when you do gradient descent, the inductive bias of gradient descent itself is during the training path to first fit the largest singular directions. So you first fit to the subspace of the largest, then the next, then the next, then the next, then the next. So it's as though you are smoothly doing an ordered fit to subspaces. You see that? So gradient descent, as it goes, is selecting. So if you think about the subspace is telling you the implicit complexity of that model. How many degrees of freedom are there? Like how complicated is that model? If you're fitting a subspace with one vector, you're fitting like a single direction. So gradient descent has an implicit bias, right? An implicit inductive bias that says the path of gradient descent will walk through a sequence of subspaces, a simple model, then a more complicated model, then the next more complicated model, then the next more complicated model, then the next more complicated model. And it'll keep doing this as you go. This is if you just do OLS. Now, notice here, in the ridge formula, what lambda is doing is also effectively cutting off subspaces. So it's also doing that. So you adjust the lambda, you're smoothly saying, well, I want a model of this complexity and not larger. Is that clear to everybody? This is important to understand. So gradient descent, because of this behavior of exponentials and time constants, also does something like offering you, as gradient descent is running, a choice of models of increasing complexity as you go. An alternate view of this is to say, when sigma I is very, very small, right, this thing is very, very close to 1. And when this thing is very, very close to 1, you can think about the whole thing as being like an integrator and just integrating this guy, adding it up at a very small slope. And so why very small slope? Because here's the sigma I in here. So sigma I is small. This thing has a very small slope. And it's as though this is just 1. So you're just moving very, very slowly like this. At some point, you'll see the exponential curving and asymptoting. But after a very long time, if you're moving very slowly. So this is why so we gave you a homework problem where we say gradient descent doesn't go nuts. Right? And there, we wanted you to do it using coarser tools. But this is like a more refined view that shows you gradient descent doesn't go nuts. Directions that are not very well represented, as the learning rate is small enough, will basically not even show up in your model. Okay, any questions on this? Yeah?
When should we use the closed form solution of OLS or ridge versus when we use gradient descent stopper?
Excellent questions. The question was, when in practice will you ever use the closed form solutions? And when will you use gradient descent and just track and stop early whenever you need to? It depends on context. To 0th order, like the basic thing, when you're using deep learning models, you will not use the closed form solution of ridge. You'll always train everything using gradient descent. Okay, that's like the 0th order view. But it turns out, in some settings, you want to use the formula because it's a heck of a lot faster if things aren't too big to use it. The number of steps, if you actually want to get the whole solution and you're cool with that, getting the actual solution, and you don't want to cut it off, if you know where to cut it off, if you know what the lambda to use is, then sometimes this can be a lot faster if d is small to do this. So sometimes you want to do that. Here's the other cool thing. We'll talk about it later. This formula can be written in PyTorch. This formula is itself differentiable. So sometimes you can use the formula itself as a layer and say, okay, go ahead and take derivatives through it and accelerate certain aspects of what's going on and adjust the focus of your model. So this is another aspect, another analogy which is useful to think about. We think about inductive bias. We want to think about what kind of stuff does our model learn. And the classical perspective on this, sort of before the modern era, which I'm going to date as being 2012 onward, was, okay, what kind of things can you represent? But when the focus shifted to understanding, well, what kind of things do we actually learn, you need an analogy. So one analogy is sometimes thinking about how you take pictures. And you can think about the learning, the model, and the optimization as being like a lens or optical apparatus. And what they do is, given data, they bring different patterns into focus. And if you think about your analogy of lenses, right? As you adjust the spacing of the lenses in your optical system, different planes will be brought into focus on the thing you want to capture. In that same way, the adjustment of the model, the optimization algorithm, and things you do are bringing different patterns into focus. And that's the name of the game of deep. That's why we have all these architectures. That's why we adjust all these things. It isn't about what the model can express. It's about what that model brings into focus. This is one perspective. Another perspective, related, is the kind of musical instrument perspective, which is closer to what's going on mathematically. So a musical instrument resonates in certain ways. And so you have a bell. You hit the bell with an impulse, but then it rings at a particular tone, right? So remember, spectra are called spectra. It's called the SVD, right? And related, you call these things like related to spectra because they are like frequencies. And so the fact that that gradient descent will sort of, for a model, will fit the high energy parts first is like saying the model resonates at those things. And the data pattern that comes into it, excites the model, but what you learn is the combination of the bad thing that comes in and where the model resonates. So that's another perspective on what's going on in deep learning, is you're crafting a kind of musical instrument. And what you want it to do is to bring out a certain quality of sound by resonating that way. This is different from the classical view of what matters is constraining capacity of models. This is not about the capacity of models. It's about their inductive bias. Okay, so these are additional analogies that are useful to have in your repertoire of how to think. So usually, like in many classes, you're told this is the right way to think about X. Unfortunately, we don't know the right way to think about everything, so I'm going to tell you lots of different ways to think about things because you have to navigate between them. Okay, so important thing is that kind of closing out this part about gradient descent in OLS is because the gradient descent will go through effectively a sequence of models that are different, early stopping looking at checkpoints of your model as it's trained and saying, hey, how good was that one? And deciding to stop and use one of those instead of the final converged model, the reason that's useful is because it has the same regularizing effect. So this is a very, very important thing in practical deep learning. You'll often do this. You won't just train a model to convergence and then use the final thing. You'll look at checkpoints along the way. Okay? So this is another kind of regularizer. Okay, any questions on that? Okay, good. So now, we spent a lot of energy and time kind of thinking about these linear models, and we did this to sort of hopefully help you understand that there's something about these linear models and the inductive bias which is really important. The MSB thing, the most significant thing that then seems to happen is what is the singular value structure of, in this story so far, of this thing, x. What is x? X is your matrix of inputs, of your features, right? So it's how your features like show up in terms of their singular value structure that determines what these kinds of algorithms will learn. Okay, so that's the lesson we've learned from all. So now we need to have a way to bridge to nonlinear models, deep models. And for that, we're going to use this local linearization point of view, which I introduced at the end of last lecture. I wrote something in the ed for, but I want to make sure everyone understands it. And we'll talk about it in the context of an example. I think you did a little bit in discussion also related to this. So let's move this over. Then I want to get into initial. That will then help us understand something that we want in initializations. Okay, so a general model that could be deep, this is like following what I wrote, is I have a bunch of parameters theta, I act on inputs, and the model emits something. I want to learn these. Okay, this is like our story. I'm going to do gradient style algorithms. So the important thing is this general model is deep and nonlinear. So now when we say nonlinear or non-affine, we mean it's nonlinear in what? It's nonlinear in x, the input. Why? So you can have expressive power and actually kind of capture the patterns you're interested in relative to the inputs. Right? You don't want to just be a linear function of the actual input. But it's also nonlinear in theta. It's not just a linear function of the theta, it's a nonlinear function of the theta. Nonlinearity in theta, or non-affineness in theta, is inevitable whenever you have a deep network. Because in a deep network, some layers are inputs to the next layer. And so if the layer is doing something nonlinear, even if the weights were acting in an affine way before, now they're going to be nonlinear coming out. So generally, you'll get nonlinearity. So now, you want to learn theta using training data. And when we talk about a local linearization, right, we're talking about a local linearization where we say, let me look at f at theta naught plus some small variation around it on generic inputs x. And we're saying this thing is basically the function at wherever you're thinking of the anchor place being, acting on x, plus this derivative evaluated at theta naught, acting on delta theta. This is local perspective. This thing is par f theta 1, or theta 1, first parameter, all the way out to however many total parameters you have in your model. Right? It's a big thing filled with partial derivatives. So if you look at this approximation has only learnable things. Like as you do a step of gradient descent or a few steps of gradient descent, the only thing you're actually going to be changing and learning is this. These are the learnable parameters here. Locally learnable parameters. This is just where you're starting. Right? There's nothing locally that's changing here. Of course, you're changing theta as a whole, but you've decomposed it this way to have this local versus like where you're anchored split. So in this, after you do this approximation, what you get is a generalized linear model where these guys are the features. Okay, they process x, because each of them takes as an argument x, right? Because it's a partial derivative of this. But you use them by taking a linear combination. So now the model is a generalized linear model, locally. It's not deep anymore at all. It's flat. Right? It just has a width of d, different things that you're learning weights on. Okay, I posted this I mentioned it last time, but I want to make sure everyone understands it. Any questions about this picture? Yeah?
Could you explain again why the derivative of respective data represents non-linear features of x?
Sorry. So I'm just saying this thing is these derivatives. These are all what? These are all functions of x. Right? That's what it means to take this partial derivative. So they're functions of x. All functions of x we call features, if we're going to use them for learning. Right? That's what it means to, what's a feature? Feature is some function of your input. Could be the 7th coordinate, that's like a trivial kind of feature, or it could be like add all the energy, or it could be any kind of weird nonlinear combination of things. So it's like a lifting. It's a lifting of x. So you can view these as being features. So this points to something really important, which is that when you have a deep model, and someone asks you, what are the features your deep model has learned? There's actually two different points of view on what that means. One point of view is the point of view expressed by this expansion. It says, well, however it is, I've trained my model, I've learned some theta naught. If I'm going to view this model as something which acts as an initial condition, as a starting point for fine-tuning, which is how we use modern pre-trained models today. If this is going to be used for optimization, and I'm going to allow myself to tune all those parameters, then the features I've learned are actually these guys. Because that's what the optimization sees. The optimization just sees these guys. Because the optimization is acting locally and taking derivatives. So it doesn't see anything else. It just sees these. And so it's going to be, this is d of them, right? it's going to be the singular values and the singular vectors associated with this lifting on your training set that determines what kinds of stuff are going to be brought into focus by gradient descent and not. Do you see that? Okay, so it's this thing that determines these derivatives. So these derivatives, interestingly, are also what PyTorch calculates. Right? PyTorch calculates what is the sensitivity to, your model with respect to a certain parameter by doing backprop. So these are things that PyTorch is also calculating for you all the time. That's how it does the optimization. So this is one view of the features. So these are, let's call them the local features for learning. Now, there is another sense which is not unrelated to this sense. So I'm going to draw a picture for that to make sure you understand that one too. So in a deep network, right, a deep network looks like this. I'm just going to draw it. I have some input x. There's some layer, right? It has some weights, it has some biases, it has lots of stuff inside of it, and it has a bunch of outputs. Those go into the next layer, which also has some weights, some biases, and some maybe different number of outputs, right? And then it goes into another layer, right? Which has its own weights and its own biases, and so on, until finally, at the end game of this, the end of your neural net, how do you cap a neural net at the end? What happens is I have some set of, so some weights, some biases, I have some set of outputs that come out, and then I add a linear layer. That generates something. It's usually a structure of these networks. A bunch of stuff happens, nonlinearities, ReLUs, whatever, stuff happening in here. Then I have a linear layer. And then something comes out. And then I attach this to a loss in some way. Right? This gets attached to a loss. For training. Is that clear to everybody? Okay. So this linear layer has its own features, its own weights associated with it. Let's call them weight linear. One perspective, a different perspective on the features learned by the neural net, is to say that what the neural net has learned is actually these different features that correspond to these outputs right before the linear layer. So you can call this the last layer, and this is like the penultimate layer. So the outputs of the penultimate layer, the last place where nonlinearity showed up, right? Those are also viewed as the features that the network has learned. Because after this point, it's just a linear model. Do you see that? There's like two different perspectives. This is saying that when I look at the entire thing, I have a bunch of nonlinear stuff, which is some kind of learned lifting, and then I have a linear model at the end. This other perspective says, actually, I have a local linear model where I have d different features, nonlinear features, corresponding to all the weights and biases. So there's models of different sizes, these two different views. So this view is also a view that you will see represented. And so when you use a deep model and you freeze a bunch of weights and you don't train them at all, and you just train a new linear layer at the end, that corresponds to one perspective. And if you tune all the weights in your model, that corresponds to this other perspective. So there's two different perspectives, right? One is this local features for learning perspective, and the second one is penultimate layer. The outputs of your penultimate layer are the learned features. And this says the learned features are these local derivatives. Does everyone see how these are two different things? They're like different numbers of things. Very important. Like they're completely different. Like they're not just like D things, but they're different. It's like this could be like 27, and this could be like 100,000, right? So it's like two different size objects. Okay, yeah, question.
So when people say they're fine-tuning a model, does that mean they're just training that less linear layer?
So when people say they're using a model, standard deep learning terminology is they say I'm using a pre-trained model. If they say I'm using a pre-trained model and they don't use the word fine-tuning, then they typically will mean I'm just adjusting this linear layer. If they say I'm using a pre-trained model. If they say I'm fine-tuning a pre-trained model, then they're often adjusting everything. We'll talk a lot more about this later. That's like a major topic for the class because it's very useful. But now this helps you see like what the difference is. But I want to connect the two together to show you that they're not entirely disparate. So associated with this linear layer are a set of weights, right? What is the derivative of this with respect to these weights? Remember, linear layer means I have a bunch of weights and I add them up. So what are these local features corresponding to that linear layer? So let's write it out. This function f at the end is a sum over I equals 1 to 27, however many the things there are here, right, of wi final layer times gi of x. So what is the partial derivative of this with respect to w3? gi3. So in this set is included these outputs. So this is a subset. This perspective is a subset of features in this, a strict subset. So these are also derivatives. Because the derivative of something linear is just the thing that multiplies it, right? That weight, which is actually the output here. Okay, is this hopefully is much clearer now to people what's going on here? So now for the case of a ReLU network, you can actually compute what these guys look like. Did you guys do this in discussion? Right? Did you plot them? Right? And you see that they have interesting shapes. Right? They're not just like, corners, elbows. Like some are discontinuous, right? They're like constant, 0, and then there's something that corresponds to the bias, right? And then some are interesting where you have, you move, then you jump, and then you go. So these are much more interesting shapes than just what you get with the ReLUs. And the homework has you also doing this. And the next homework will have you doing more of this. So this is so you can get a sense for what's going on here. But yeah, so if you want to understand fine-tuning, you need to know what are the singular value structures on your training data of these guys. If you want to understand simply using a pre-trained model and what it will learn, you look at the singular value structure of these guys and see what it'll learn with gradient descent. Okay, so I have gone slower than I expected, but that's fine because I have Monday to catch up before discussion. So yeah, what I want to say next is that once you have this picture, you can now begin to understand if you're going to look at initialization. So one thing is to look at this after you've trained it. But the other thing is to make sure you can train it to anything at all interesting. So that requires to understand how does this thing behave at initialization. So it's very important to understand at initialization what this guy looks like and behaves like. And that's the thing that drives the choices of how you randomly initialize your network. You want to make sure this thing will behave nicely. It won't go cuckoo on you. And that we'll talk about next time. And we'll talk about optimizers next time. Okay, I have office hours now. Any questions on the stuff on the board I can answer right now, and then we can move over.